everyone, welcome back to Newtonian Nation. We, the physics students of Sri Ramakrishna College of Arts and Science, are extremely happy to be presenting the fourth episode of Muon g-2 particle physics experiment series. In this video, Harish and I will be explaining about the theoretical evolution of Muon g-2 experiment. In previous video, Bhumika had explained about the experimental setup. If you haven't watched it already, make sure to watch the video. And now let's get the video started.
Any object moving in a straight line exerts a momentum on that object. P is equal to mv. Momentum is equal to mass into velocity. If that object moves in a circular path, then its momentum is known as angular momentum. L will be equal to mvr. Angular momentum is equal to the product of mass, velocity and radius of the circular path. But a charged particle moving in a circular path causes a magnetic moment on that particle, specifically called as the magnetic dipole moment.
Magnetic dipole moment is calculated by the formula M equals I into A, that is the product of current to its area. I is given by the formula Q divided by T, where Q stands for the charge of Muon, that is the same of electron, and T is given by the formula 2 pi r divided by V, and 2 pi r is the circumference of circle. When we substitute Q and T in the formula for current, we get I equals E divided by 2 pi r divided by V, and when V goes up, we get EV divided by 2 pi r. And as we know, the area of circle is pi r square. When we substitute A and I in the formula for magnetic dipole moment, we get M equals EV divided by 2 pi r into pi r square. When we solve this, we get M equals EV divided by 2 into r. When we multiply and divide by M, we get M equals E divided by 2m into mvr. As we know, mvr stands for angular momentum. It could be replaced by L, and we get M equals E divided by 2m into L. Before moving to the next part, let us know what is Dirac equation. In simpler terms, it could be said as it is the equation that describes the behavior of fast-moving objects, and it also predicts the antiparticles.
The anomalous magnetic dipole moment of the electron, which is so-called g-2, provides us with a high-precision test of quantum electrodynamics. Here, we use Dirac equation to solve this problem by adding another factor which is known as the g factor.
I hope you would understand the theoretical formula for calculating magnetic dipole moment. Now let's calculate the theoretical prediction of Muon g factor and anomalous magnetic dipole moment. From the above formula, we can understand that 5 values are needed to calculate g factor. In that, 4 are constants, that is E stands for elementary charge constant, h bar is reduced Planck constant, m is mass of Muon, s is spin value of Muon.
The fifth one is magnetic dipole moment. We already knew the formula. In that, r is the radius of circular magnet. It is around 7.62 meters, and n is the density or number of particles which come out from the muon collider. It will be calculated from the quantum free electron theory, and that value will look like this. With radius r and density n, we can find the magnetic dipole moment. With the help of all these values, we can find the g factor of magnetic dipole moment of muon. The anomalous magnetic dipole moment is calculated from the g factor. A is equal to minus 2 divided by 2.
Precise measurement of this dipole moment of Muon and its comparison to theory allows us to study new physics phenomena beyond the standard model of particle physics.
And this is how the g factor and anomalous magnetic dipole moment are theoretically being predicted. With this, we come to the end of the episode. I hope you guys enjoyed watching this video. In the next and final episode, Snega and I will be explaining the final result of Muon g-2.